Hey everyone, welcome back. This is lesson 9.1, multiple representation of functions. The objectives for today, you're going to be able to translate between the various representations of functions, and you'll be able to solve problems by using the various representation of functions. In this warm-up, I'd like you to create a table of values for each function. And really the main thing I want you to remember when you're creating a table is you get to choose whichever x's you want and then solve for y. So here I chose 1, 2, 3, 4, and 5, and then just inserting the 1 for x and then 2 and so on, we get our y values. Same with the second function. We get to choose, and I always choose the easiest one, so I chose 1, 2, 3, 4, and 5, and then substitute for your x's, and you solve for your f of x. Take a look at this situation. An amusement park manager estimates daily profits by multiplying the number of tickets sold by 20. This verbal description is useful, but other representations of the function may be more useful. For example, you could write this information as an equation or a function. The profit equals 20 times n, the number of tickets. You could also write it as a table. For every 50 tickets sold, your profit is going to be 1,000. And every 100 tickets, your profit will be 2,000, and so on. Or you could draw it as a graph and see it visually this way. These different representations can help the manager set, compare, and predict profits. All right, this example problem is going to be similar to the ones you'll be doing in class today, and maybe in the real world. It's a business application. It says sketch a possible graph to represent the following. So the following says ticket sales were good until a massive power outage happened on Saturday. That was not repaired until late Sunday. All right, so that's all the information you're going to be given. So you'll need to think about what's actually happening here. And we know that probably the graph is going to show a decreased sales until Sunday. So I'm just going to draw a sketched one, and then I'll show you what their answer actually shows us. So let's start with Friday and Saturday and Sunday and Monday. All right, so let's say we had sales, it doesn't even matter. You can just make up anything, 1,000, 2,000, 3,000, 4,000, 5,000. We can make up anything. It doesn't matter. We just need to be able to show what the picture looks like. So on Friday, the ticket sales were good. Okay, ticket sales were good. So let's put Friday way up here. All right, and then a massive outage happened on Saturday. So we know that we're not going to have very many sales. So let's put it way down here, Saturday, okay? And it was not repaired until late Sunday. So it's probably going to stay low because nothing's going to happen on the next day. But then on Monday, the sales are going to come back up again. All right, so our graph is going to look something like that. And here's a more precise look might be. Yours does not need to look perfect like this. It could look like mine, but it does need to be neat and on grid paper. But you can kind of make up whatever numbers you want here, and you do need to label amusement park sales. You need to label things very clearly, but as long as the graph is doing pretty much what the narrative tells us, notice that they're pretty much the same, then that would be correct. So here's one for you to try on your own. It says, what if? Now sketch a possible graph to represent the following. The weather was beautiful on Friday and Saturday, but it rained all day on Sunday and Monday. So think about an amusement park. What's going to happen at an amusement park? Go ahead and turn your video off and try that and see how your graph compares to the one that the book came up with. Okay, so I hope you were able to come up with a possible graph to represent that. And here's we know that the graph is going to show decreased sales on Sunday and Monday because it rained all day on Sunday and Monday. So notice, and again, yours doesn't have to be the exact, but it should look something in this form where the weather was beautiful on Friday and Saturday. So Friday, they figured good sales. Everybody's out of school on Saturday, so even a little bit better. But then notice on Sunday the sales drop way low and stay low on Monday because nobody's going to be in the park on those days. So as long as your graph looks something like this, it doesn't have to be exact, but it should at least show that there was some kind of a decrease. This is the main thing I'm looking for, is that there was some kind of a decrease in sales on Monday and Tuesday, or Sunday and Monday. right, here's another one for you to try on your own. Sketch a possible graph to represent the following. Only half of the rides were running on Friday and Saturday. So go ahead and turn your video off again and see if you can draw a possible graph of what that might look like. Okay, so if only half of the rides were running on Friday and Saturday, that tells us that the graph is going to show decreased sales on Friday and Saturday, because who wants to go to a park on Friday and Saturday if only half of the rides are running? And a possible graph might look something like this. On Friday, it was low because only half of the rides were running. But notice on Saturday, all the rides are running, so we're a little bit higher. And then on Sunday, we only have half rides again. Half of the rides are going, and then back up a little bit more on Monday. And notice they put it not quite as high as on Saturday because most of the kids might be in school or something on Monday. It's usually just a low day at the park. So again, as long as you are showing an increase like this and a decrease like that, your graph would be correct. You don't have to have exact numbers here. You can make up your own. It doesn't matter. Friday, Saturday, Sunday, those days would need to be labeled correctly, and our day and sales. Because each representation of a function, words, equation, table, or graph, describe the same relationship, you can often use any representation to generate the others. For example, all right, Janet is rowing across an 80-meter wide river at a rate of 3 meters per second. The question tells us to create a table, an equation, and a graph of the distance that Janet has remaining before she reaches the other side. When will Janet reach the shore? All right, so we have to create all three of these to complete the assignment. So the assignment says create a table. Let's do that one first because that's probably the easiest. So we can just set up the table and let T be the time in seconds and D be Janet's distance in meters from reaching the shore. Janet begins at a distance of 80 meters and the distance decreases by 3 meters each second. So you can see at 0 seconds she's still 80 meters away. At 1 second she's now 77 meters away, and at 2 seconds she's now 74 meters away. So our table is pretty easy. Now you can put that in your calculator to come up with an equation, or you can just come up with it on your own. So let's take a look at how to write the equation. All right, so step 2, we're going to write an equation. And when we think about it, we see that the distance is equal to 80 minus 3 meters per second. So to write that as an equation, it's pretty simple. D equals 80 minus 3t, 3 times the time. All right, so the next thing we need to do, now that we've created a table and an equation, and let's remember what our equation was. Our equation was D equals 80 minus 3t. All right, so the next thing we want to do is find the intercepts to graph this, because our last thing to do is we have to make a graph. And the easiest way is to do your intercepts, and I would say time and distance. And to do your intercepts, we always say, what is time when distance is 0? Or what is distance when time is 0? So we're going to substitute at the beginning, we're going to substitute D for equal to 0, and then we'll also substitute T, so with 0. So the D-intercept is 80, because when T is 0, let's do this one first. When T is 0, the whole thing is 0, so D equals 80. All right? And now we could also solve for T, so let's set D equal to 0. And when we do that, we see that 0 equals 80 minus 3t, subtracting 3t from both sides, and then dividing by 80, we end up with t equals, the time is 26 seconds, 26 and 2/3 seconds. All right, so that's going to be our t-intercept, which is 26.6 actually. And now that's a pretty easy thing to graph. So now we just find when t is 0, she's right here at 80, and when t is 26.6, way over here, then the distance is 0. So there we go. We can plot that, and there you go. All right, try this problem on your own. Turn the video off and give it a try. All right, so this table shows the height in feet of an arrow in relation to its horizontal distance from the archer. Create a graph, an equation, and a vertical description to represent the height of the arrow with relation to its horizontal distance from the archer. So, first of all, we need to understand what the question said. So we have an archer here, and he is shooting off an arrow, and it's going to come like this and then hit the ground. So we're trying to figure out how high is it compared to the distance away from the archer. So we want to know what's happening on all of these places. And generally, when we think about things getting shot off, or rockets or balls or things, usually those travel in the path of a parabola. All right, so it's going to get as high as it can and then start tapering down again. So in this case, we've already been given the table, and so we're going to need to create a graph and an equation and a verbal description of what's happening. So here's our table. Let's move on. And the first thing that we should do is use the table to check for finite differences. And notice that the finite differences on the first differences, when we subtract each of these, 47, 85, 85 to 98, and so on, we get these numbers, our first differences, all right? When we subtract again, notice that they're all 22.5, 22.5, 22.55, pretty much the same. So when we have second differences that are constant, that are the same, we know that we probably could use a quadratic equation. So using your calculator, we can use the quadratic regression feature to write an equation. Okay, so continuing on with this example, the second thing we need to do is use the quadratic regression feature on your calculator, and we end up with our equation here. And then finally, we need to use a verbal explanation of what happens. So let's take a look at our graph once you have it in your calculator. And the graph of the equation, so here's your verbal explanation. And you would need to write all these down in words. So this is going to be part that you will write in words. So let's see what happens. It says the archer shoots the arrow from a height of about 6.52. Now, how did I get 6.52? Well, I looked at my equation up here, and I see when x is 0, this whole thing would be 0, and this would be 0. So my y tells us where I'm starting. Okay, my y-intercept here. So it tells me I'm starting at 6.52 feet. It travels horizontally about 220 feet to its peak. So about here, all right, if this is 500, this is close to 220 feet to its peak. Height of about 99 feet. So here's our 99 feet. And then it lands on the ground about 500 feet away. Now notice 500 is here. It's not exactly 500. You don't have to have exact terms, but you need to be close to giving a good description of about what happened. All right, so here's a page. It also can be found in your book. This will just kind of help you think about what to do and how to try and solve things and what order to go in. This is also found on page 656. Page 656 in your textbook if you'd like to take a look at that and save that. So these are just different things to try when you have to when you're given a table, what things to do, a graph, equation, and verbal description, and so on. And you can turn the video off and read that on your own. All right, so remember, the point-slope form of an equation of a line is y minus y1 equals m times x minus x1, where m is the slope and x1 and y1 is a point on the line. That's that equation will come in really handy for you. And also you can remember first differences are constant in linear functions and second differences are constant in quadratic functions. All right, and again, that's from lesson 5-6. Okay, here's an example. A hotel manager knows that the number of rooms that guests will rent depends on the price. The hotel's revenue depends on both the price and the number of rooms rented. The table shows the hotel's average nightly revenue based on room price. The question says to use a graph and an equation to find the price that the manager should charge in order to maximize his revenue. So when we graph out this information, it looks like it doesn't appear to be linear. So first thing we're going to do is check for finite differences. So in doing that, we take our revenues and find the differences between them. And we see the first difference is they are not constant. It's not finite. All right, so our second differences are, notice they're both 400. So we finally found a constant there when we subtracted. And so because the second differences are constant, a quadratic model is appropriate. So use a graphing calculator to perform a quadratic regression on the data. All right, so once you put it in your calculator, you should see something like this. And so what we can do now is just realize that the equation is negative 2x squared plus 440x, models the data, and the graph appears to fit. Use the trace or maximum feature to identify the maximum revenue yield. The maximum occurs when the hotel manager charges $110 per room. So that's going to be our highest profit right there. All right, a new example. An investor buys a property for $100,000. Experts expect the property to increase in value by about 6% per year. Use a table, a graph, and an equation to predict the number of years it will take for the property to be worth more than $150,000. So the first thing I want to do is draw a table and a graph. And so in order to come up with my table, I'm going to think about what's happening each year. At year 0, I have 100,000. By year 1, I have 106,000. How did I get that number? Well, I know 100,000 times 1.06 is 106,000, and so on. So I take each of these amounts and multiply it by 1.06, all right? And so that's how I get my values for 4 years, all right? And then I can also graph that, and I can kind of see what's happening. It looks maybe kind of linear, maybe exponential. Doesn't really look too quadratic to me. So let's think about the formula for interest. And remember, we had a formula that said A equals A1 plus or minus the rate raised to the time. And notice that's going to be an exponential because the variable is as an exponent. So that's going to be my first clue as to what this kind of equation I'm going to need. But what I should do is go ahead and take a look at the data, and it appears to be exponential. So I want to check for a common ratio. So what I'm going to do is take all of these amounts and divide them each, and I see that each of them were equal to the ratio is about 1.06, which is what the interest rate is. So I can easily go ahead and put in my calculator and solve for this equation. Because there's a common ratio, an exponential model is appropriate. Use a graphing calculator to perform an exponential regression on the data. And when you do that, you can see that our A starts out at 100,000 and it is multiplied by a rate of 0.06 and to the x power. And so there's your equation. Now we want to know when it's going to reach 150, so you can use your trace, the trace feature to identify the value that the x corresponds to 150,000 for y. And it appears that the property will be worth more than 150 after 7 years. And I usually don't use the trace. I usually just go in and look at the table, but you can do it either way to find when that happens. All right, here's one for you to try on your own. Turn your video off and give it a try. So this problem says Bartolo opened a new sporting goods business and has recorded his business sales each week. To break even, Bartolo needs to sell $48,000 worth of merchandise in a week. Assuming the sales trend continues, use a graph and an equation to find the number of weeks before Bartolo breaks even. So I have to kind of think about what kind of equation do I think this is going to be. Do I think it's going to be a linear equation? Do I think that's going to act kind of something like that? Do I think it's going to be a quadratic equation that will look something like that? I hope not. I don't want my sales to do that. Or do I think it's going to be exponential, where it's going to go up like that? Well, I hope that it would be exponential because I want to get more profit quicker. So I'm going to guess that it's going to be exponential. But before we do that, to find out, we check our ratios to see if these ratios are the same. So I take 25,000 divided by 27.5, 27.5 divided by 30, 30 divided by 33,275, and so on. So I'm going to see if I have a common ratio there. And so when I do that, I see, yes, there is actually a common ratio. It's 1.1. All right, so now that I have that information, because there is a common ratio, an exponential model is appropriate, using a graphing calculator to perform an exponential regression on the data. All right, and so once I put it into my calculator, I can see that the exponential formula is right here. Here's my equation. All right, and you might need to enlarge your window. You can use on your zoom button, you can use zoom stat or zoom fit and get it to where you can see the points better. And so here's a small graph of this. It says the equation y equals 22,727.15 times 1.1 to the x power models the data, and the graph appears to fit. Use the trace feature to identify the value of x that corresponds to 48,000 for y. So you can see he will break even after 8 weeks. And again, I often just use the table function, the second table on my calculator. For me, that just seems easier, but either way is fine. All right, and that's the end of this lesson. Here's one more little quiz you might want to try and see if you remember this. It says the graph shows the number of cars in a high school parking lot on a Saturday beginning at 10 a.m. and ending at 8 p.m. Give a possible interpretation for this graph. So go ahead and turn your video off and try that. All right, so a possible interpretation, that just means using words, what you think might have happened during the day at the high school. Here's one example. It is not a be-all, end-all perfect answer. It's any answer, any idea that you came up that might fit the information. So a possible answer would be football practice goes from 11 a.m. to 1 p.m. So obviously there would be more cars in the parking lot between this period of time here. Families begin arriving at 4 p.m. for a play that begins at 5. So we can see that there's not too many people in the parking lot here, but then the play starts at 5 and it goes to 8, or it ends at 7, and then after the play, most people leave. Now, some people might leave their car in the parking lot and go get pizza or something afterwards, so all of the cars might not be gone yet. This is just an example of something you could have come up with. You might have come up with something different. As long as it follows the same pattern, you're working out good. All right, and that is the end of our lesson for today. This was lesson 9.1, multiple representation of functions. And I hope you have a great day, and I'll see you soon. Bye.